Partial differential equations, or PDEs, are essential tools used to model phenomena in our universe. I originally started to list all their applications, but almost all physical models incorporate PDE at some scale, though it is often simplified to much simpler models that most people can solve with simpler tools. While there are a number of videos on individual equations and how they work, the goal of this video is to highlight a variety of them, and to rate them on a completely biased basis. If I were to do a deep dive video on the equations I mentioned in full detail, it would turn into one of those 12-hour video essays that might as well be a book, and there are already better books out there discussing the properties and applications of these PDEs. Before we start, I must say that there are way more PDEs than I can cover here. This video simply highlights equations that I've encountered in my studies, in my work, or just reading about them. All of them are amazing and useful in their own right, and this ranking is purely personal preference. If I missed your favorite PDE, or you disagree with one of my rankings, let me know in the comments. If I miss enough PDEs, I might have to read about them and put them in the tier list at a later date. Let's kick things off with the three equations that dominate most Introduction to PDE courses. These are the prototypes for many other equations, and without them, our understanding of PDEs as we have them today wouldn't exist. That being said, I don't have to be particularly nice to them. Laplace. The Laplace equation describes systems in a steady state, such as electric potentials or gravitational fields in regions without sources or sinks, instead being dictated by the boundary conditions. It's the go-to example of an elliptic PDE, which usually means time is ignored. A concept, when I'm modeling things, is not something I'm a huge fan of. Add the fact that there are other popular elliptic PDEs that do this introductory job better, leaves me little choice but to put it in at C tier. Wave. The wave equation models the propagation of waves of many flavors, such as sound, light, or water. As the classical hyperbolic PDE, one might expect a higher ranking than the Laplace equation because it operates in both time and space. But there is a simpler way to introduce hyperbolic PDEs, which I'll cover later. As it's not a particularly great prototype, it is also going in C tier. Heat. The heat equation describes the diffusion of heat or other substances over time. It is the quintessential parabolic PDE, as I don't know of any simpler or cooler prototypes, but it lacks that je ne sais quoi to deserve a top spot. Still, congratulations to the heat equation for being the inaugural member of B tier. Poisson. So I think this equation is cooler than the Laplace equation in that it covers the inhomogeneous response, or basically the response of gravity to masses, or in electric fields to charged particles. Going forward, I won't make the distinction of a homogeneous or inhomogeneous equation, but since this distinction is so often recognized in the literature, I will do the same. As such, I have to give it a higher rank to this one because it is significantly more useful. I would put its cool factor at about the same level as the heat equation, which puts it in B tier. One-way wave. The one-way wave equation simplifies the generic wave equation, where activity propagates in two or multiple directions, so that all activity instead moves in just one direction, simplifying its characteristic curves. As such, it is easier to analyze and solve than the regular wave equation, presenting a stronger case of being the prototype hyperbolic equation. And while it's less ubiquitous than the generic wave equation, it still has its uses in signal processing in systems where the direction of a wave is known beforehand. As a proper prototype, I will place it in the same level as the heat equation, B tier. Helmholtz. This is another elliptic equation, of which the Laplace equation is a special case. It's an eigenvalue problem, a huge plus, and it also has a wide range of applications, including solving the wave equation. Since it clowns on both the Laplace equation and the wave equation at the same time, I think A tier is a fitting spot for it on this list. Now we're going to move away from the equations you might see in an introductory PDE course to ones that might show up in a physics or engineering course, where computational methods are more common tools of analysis than mathematical arguments, especially for those who work with them on a day-to-day basis. KPP equations. These equations combine reaction terms for growth with diffusion to spread material throughout space, with various assigns for reaction rates. They're widely used in ecological and chemical modeling. I love how they balance simplicity with nonlinear complexity. It keeps things interesting yet manageable. Solid A tier. Navier-Stokes. These describe the motion of viscous Newtonian fluids and are widely used because many fluids are approximately Newtonian and the length scales are such that viscosity can play a role. Because of its popularity, there is even a $1 million Millennium Prize for proving the existence and uniqueness of 3D solutions to these equations. This $1 million prize puts Navier-Stokes on a pedestal, overshadowing other great fluid PDEs, and even PDEs in general. For some evidence to this point, I asked ChatGPT what it thought the coolest PDEs were, to get a sense of what popular PDEs are, and what do you know? The top of this list was Navier-Stokes, followed by the heat and wave equations in 3rd and 4th place. So Navier-Stokes joins the latter in C tier. The other equations in ChatGPT's top 5 answer are also in this video, which I will mention when I come to them. Euler. This is Navier-Stokes without viscosity, but these were among the first partial differential equations to be written down, which is something to be expected when something is named after Euler, which makes it a mark against it. It is a good starting point for other fluid PDEs, many of which I've studied during my dissertation. As such, I put it in B tier. Oldoroid B. Oldoroid B is a fluid model used to capture viscoelasticity, an example of a more complicated constitutive model than Navier-Stokes. It was foundational for other fluid models that I studied during my undergraduate research. The only knock I have on it is that its name wasn't swapped with a similar, but less famous Oldoroid A. Only one of these has a Wikipedia article if you want to know which one is the important one. Still A tier though. Rotating shallow water and viscid primitive equations. The primitive equations apply realistic approximations and features to the Euler equations for atmospheric dynamics, like hydrostatic balance, the Coriolis force, and the ideal gas law. The shallow water equations simplify things even further, reducing the 5 equations down to 3. Since these formed the backbone of my dissertation on atmospheric dynamics, they open up S tier, though in this case S might stand for Stockholm Syndrome. Inviscid burgers. This equation is quite cool. It either has an implicit solution, a rarity for a nonlinear PDE, or it forms a shockwave, which is a whole rabbit hole in itself. I came across it in research as a large-scale equation in a multi-scale model, where shocks would form, but then one would have to return to a more fundamental model at smaller scales to properly analyze this shock. Awe-inspiring. A tier. Quarter-wave de Vries. Another equation I came across in multi-scale fluid models. It is an integrable equation, meaning that there are enough conserved quantities that the motion is quite limited. One great feature of this is the soliton, a wave solution that maintains its shape as it propagates. We even have exact formula for them. As the prototype of an integrable system, it represents one of the greatest breakthroughs in nonlinear PDEs. As such, the only proper place for this is S tier. Nonlinear Schrödinger. The last of the fluid equations that I'll cover, this also emerged from my multi-scale work. Originating from a modified Hamiltonian in quantum mechanics, it shares many of the elegant properties of integrable systems. My only complaint is in its name, which shares that of another equation, which I'll get to in a moment. A tier. The Schrödinger equation. When I asked ChatGPT about the coolest PDEs, this came in at number 2, which is not a good sign, probably because it shares the name with that abominable cat. It describes wave functions of quantum mechanics, and it is hyperbolic despite looking parabolic. The only thing that saves it from C tier is the hydrogen atom solution, one of the coolest analytic results ever, with all those fascinating electron orbitals, which I'm showing here. Therefore, it belongs in B tier. Klein-Gordon. Klein-Gordon results from trying to unify quantum mechanics to special relativity, which in operator form basically spells out the full E squared minus PC squared equals MC squared squared of Einstein fame, and the equation which describes the behavior of spinless particles, such as the Higgs boson. Since it doesn't describe spin, other equations like the Dirac and Procol equations are needed to do what Klein-Gordon set out to do. It also shows up as a relatively simple example of a dispersive wave, which is an important feature to consider in wave dynamics, and was used as such as a toy model during my dissertation. A tier. Maxwell. Oh, where to begin? These equations have been a muse for many mathematicians and physicists. They form the foundation of electromagnetism, and they inspire advancements in notation and formalisms. If you hear some Twitter moron talking about expanding quantum mechanics, and they don't include some discussion of Maxwell's equations as a basic part of their theory, you can immediately throw out what they have to say, because it's probably bullshit. That being said, there are a lot of good YouTube videos covering their perspective on these equations. For a linear equation to draw out such great work, and being such a great filter for cranks, I can only grant it S tier. Iconal. The iconal equation might be the simplest looking equation on this list, but it is still pretty cool. It plays a key role in wave propagation and snuggles nicely into the WKB method of asymptotic analysis. It's probably the most underrated equation on this list, but it doesn't do a lot to stand out, so I'm putting it in B tier. Euler-Lagrange. Including this feels like cheating, since it's more of a framework to derive PDEs from the principle of least action than an equation proper. But it has a definition as such, so I'm including it on this list. Since it can generate a whole bunch of other PDEs on this list, it has to belong in S tier. But in the same way that using a cheat code is an S tier strategy in a video game. It is so broken that it can even show why Gaussians or bell curves are so popular in statistics, in that they maximize the entropy while satisfying other constraints, seen here. Cauchy-Riemann. This might seem like a strange inclusion, but they are PDEs, even if they are mostly used to check for complex differentiability. But it still finds other uses, one of them being a way to find steady fluid flow in a given geometry. It is also a key building block in more complex forms of geometry, in that it characterizes conformal complex maps, which has a bunch of different geometric interpretations depending on how crazy you want to go. That being said, it can't oversimplify things, so I have to put it in at B tier. The Einstein field equations. This rounded out ChatGPT's top 5 coolest PDEs, but the way it is written hides too much to be considered honest. If one expands G, then expands R, tensor, and scalar, and then expands all of these out to the Christoffel symbols, you then very quickly realize, oh, this is awful. Don't get me wrong, these are important equations, but if they were named something else like the geometrodynamic equation, few outside of math or physics departments would really care much about it, only because of Einstein. Therefore, I have to put it in E equals MC tier. Fokker-Plomb. This comes out of a stochastic differential equation for an ESO process driven by a Wiener process, modeling a probability distribution moving forward in time. It is extremely important in describing all sorts of behavior from Brownian motion to chemical reactions, biological growth, finance, and information theory. Since it has such a wide range of use, putting it in A tier seems like a proper place for it. And rounding out this list, we have Black-Scholes, which takes a payoff distribution for a financial derivative, runs the clock backwards from payday to today, and tells us what the risk-free price ought to be. This turns into a PDE because the hedged portfolio takes the underlying stochastic differential equation and cancels out some stochastic parts, making it deterministic. That little trick alone is cool enough to merit it a spot in B tier. And with that, I have finished my PDE tier list. Even if I said something mean about a few of these equations, all of them deal with some of humanity's greatest insights into the physical world, so even making the list is a win in my book, which is why I didn't have a D or an F tier for this list. Let me know what you think in the comments. If you like this video, then like this video. Thank you for watching.